Invite our first guest speaker, Peer-Olaf Siebers from University of Nottingham, who I think is going to tell us about some work in agent-based modeling and DSLs for characterizing these models.
Thank you very much for the invitation. I always like to go to a new audience. I've never presented before mathematicians before, so it's very nice to meet you all. And I'm a software engineer from computer science, and I'm interested in social simulation. And there in particular in methods, how you can design models. Because we always use the same models, and maybe there are models that have more details that are of interest. And my talk today is a short introduction of what I understand by agent-based modeling, because it might be that we all understand different things. And then I talk about state charts, which is the main method I'm using. So in computer science, we have design patterns, and one of them is a state design pattern, and I use this for my modeling. Then I have developed a framework that helps to involve the community in agent-based modeling. And I want to present that to you as well, because we talked about transparency and engagement from the community so that we can get trust and credibility for our models. And then finally, I wanted to introduce you to multi-method modeling, because there are different paradigms of simulation and you can combine them. So rather than just looking at the disease and its spread, we could consider how hospitals could be embedded in our models. And we might use a different method than agent-based modeling for this. And yeah. So this is my idea of agent-based modeling. It's very similar to yours, I guess. So we have a collection of agents. They have some rules. They need to communicate with each other. And we hope that we can see some interesting system properties emerging. You can see there, I don't know, anyone here knows the game The Sims? Yeah? That's very good. So this is basically what I'm doing. I build these kind of models. The underlying technology is very similar to the models that I'm building. They have used state machines in the old days. Nowadays, because things get more complex, they use other things. But basically, you have entities that you define their character beforehand, and then you just let them run, and they interact with each other, and you can observe what's going to happen based on how you characterize your actor. Agent-based models are useful for studying social and economic phenomena, and also in operations research now they are more used. They employ bottom-up approach. They capture the dynamics of the system over time. So you're running a simulation and you can observe at any point in time what the current state of the system is, and hopefully they capture some emergent phenomena. It's very important to understand that agents don't have to represent individuals, but they can also be things like whole households or firms or organizations. Very often, if you can think that something has a mission statement, yeah, a reason for doing things, then you can probably build an agent-based model by using these components. We have seen already a state chart, which is a SIR one, but this is one from the gaming industry, and you can see different states. This is an enemy player, so he's trying to attack other people. And then, so the boxes are the states, and you have the transitions, and these transitions are triggered by something that happens in the environment. Either someone comes closer, there will be a transition, or the agent itself makes a decision based on rules, there will be a transition. So this is the basic idea of a state chart. Now we have a state. We all know what a state is. So a glass can be empty or full, or someone can be idle or busy. And we have transitions. These are movements between the states, and they require a specific trigger. And these triggers are actually the interesting thing where the complexity comes in. So state charts we can develop relatively quickly, but then we have to think very carefully why and how people transit from one state to another. And there are different types of transitions. There can be timeouts. So if we stand in front of a traffic light, after some time, hopefully it gets green and we can move on. There can be rates. This is where probability comes in. So we use probabilistic equations to actually generate these rates. There can be conditions. So if 5 people do something, I do it as well. And there can be messages that are passed between agents. So if I send a message to someone, that person will respond to it. So we can model networks and the interaction between the agents. And then there can also be something called agent arrivals. So if certain types of agents arrive, I will respond to this. Then my students always get it wrong. So I just added it here. What's the difference between a flowchart and a state chart? You saw the state chart looks very similar to a flowchart, but there is a big difference. A flowchart always defines a process. So the agents are actually inside and going through the different steps of this process. When I have a state machine or a state chart, then I look at an individual agent and I define what the states are this agent can be in. These are all the symbols. This is all you need to know. Once you understand these kind of symbols, you can make any state chart you like. So I don't want to go through them in detail, but it's basically you have the different state, and they can be states inside states. So you have compound states. Each state chart needs to start somewhere. So you need to initialize the agent, and then you can have branches, and at some point you might end up in a final state. And agents have a memory, so they can remember if they go to another state at which state they were before. Interestingly, and often forgotten, in software engineering we have objects, so we do object-oriented programming. In each object we can have more than one state chart. And one good idea is that you have a physical state chart, that a person is in a state of moving around in the world, but you can also have a mental state chart where you have emotions or something, steps that you get from a good mood to a bad mood, and that is influenced by the physical state chart. So you can have more than one state chart in an object. Now here's an example, one student project where we looked at adaptive architecture. So we wanted to see and convince architects that this is a cool new idea. Adaptive architecture in this case is that we have a museum here. We have an entrance where people come in, and then they have display screens, and these display screens will move depending on how many people are at certain places. And they will also get bigger and smaller so that you can accommodate the amount of people coming in. And then we thought, why not putting in something really cool? And we have a separation wall there. And the separation wall has emotions, and it will move trying to avoid too many people. So it will move around like people and will make decisions like these people. I have a quick video. I hope it works. Just to show you the simulation. Yeah. So here you have the people coming in, and you can see the screens are moving, and you can see the wall is moving a little bit from one side to the other. Behind this is something called the social force model. So it's a model from physics where you can see how atoms respond when they get too close to each other. And someone, a guy called Helbing, has translated that to represent human movement. And we have translated that to represent the wall movement as well. So if people come too close, the wall gets scared and tries to move away. So this is an agent-based model. You can see some statistics as well, but this is based on this state chart. Basically, we have this state chart, and then we have the motion model. And the state chart, you can see there are 2 different or 3 different compound states, and then we have the state of arriving, moving around, finding a window, reading, following the window, and usually this is a design, so you can't see that, but usually we have different triggers that trigger the transition between the states. And this is all we actually define. We don't use any mathematics for defining this. And when we implement this, as I said before, we have a state machine pattern, and that looks around if any events are happening, and if something happens, it looks what kind of event that is, and if it's relevant for this state machine, and then transits from one state to another. Behind these transitions, as I mentioned before, we can have rates or certain distributions, basically. But we can also have some timeouts or rules. So then we come to the next point. How can we build these models? How can we build it together with other people? So to gain some trust. And again, from software engineering, we have a very structured approach. So we don't do things random. You can imagine if you create something like Windows and you do things randomly, there are 1,000 people involved in the development, then things will not work. So we have a structured approach of how we design software. First we do an analysis, then we do the design, and then we get a good output. And I use this kind of technology to actually co-create these kind of models with other stakeholders. And first we define what we actually want to do, then we define what elements we need to consider, what activities they will do, we define the archetypes we want to model, and then we define these kind of state machine diagrams and some other diagrams. We define how the agents interact, and in the end we define how we want to equip our artificial lab that we are creating. When you do this, you get a lot of contextual knowledge as well when you debate with people. And you get your model in the end. So it's normally 4 to 5 participants, can be anyone, and you can see Confucius and Socrates, because it's very important that everyone can say what they want, and Confucius stands for collecting information, and Socrates stands for debates. Yeah, so there are times where you're not allowed to debate, which is very, very difficult when you have academics in the room. So you can never stop them debating. And then the moderator will normally be the modeler, and unlike normally in focus groups, they will be involved in the discussion because they know what to do, basically. And it's an iterative process, and this is very nice. You don't start empty-handed. Whenever you go to the next step, you can reuse what you developed before. So that's very good. And then if you go to a step and you feel you can't go further, then you must have made a mistake previously, and you can go back and fix that. This is what it looks like for the adaptive architecture example. I just wanted to show you an overview, and you can see the blue things are UML diagrams. So they are relatively simple to understand. We use them in software engineering to define the design of the software, but you can also use them with everyone else because they're relatively straightforward, especially if you give a little bit of advice. Now, we come to building and validating these models. So you might know the model that I'm showing there. It's also based on the state machines, and there you can see some messages being passed and some rates being calculated. And here we have networks. We have different types of networks, like small-scale networks. And the model, actually, we create a lot of objects. You can see here, we have the artificial lab, and then we can run simulations. We define our agents by deciding what we need, so which agents are relevant for the simulation. Then we define their states and behavior, put them in an environment, establish the connections between the agents, and then we run some tests that will make sure our model represents what's happening in reality. Validation, very important. I don't go through it because you know all that the model is worth nothing if it's not validated. The next thing I want to talk about is different simulation paradigms. So you will be familiar with system dynamics modeling because basically it's a collection of ODEs that you're using to look at how things change over time. And these models are aggregate. So you can see I've got a population there, and we have some flows and some stocks. Next thing you might not be familiar with is discrete event simulation, where we actually model something like queues. So if you think about a shop where you have to queue and you have some service desks there, how many service desks should you open? If you want to answer this, you can use these kind of models. We have a queue there, a delay, which can be the cashier getting the money from you, and then you're leaving. You can see there, I'm using a triangular simulation, triangular distribution to actually model the delay. So I get some stochasticity in the model. And then we have our agent-based models. And in this case, I have a very simple one, which has two states, state red and state blue. But models don't have to be super complex. So if I want to build a model in marketing, I can have potential adopters and adopters. As I said before, the complexity lies in the transition. So when do they actually change the state? Now here, I started having a multi-paradigm model. So I mixed the agent-based model with a discrete event simulation. And that's good if you want to model how many hospitals you need, for example, to treat people who are infected. You can also model how many people are actually taking the help, for example, and how many would not. And so in this case, the parameter that we are changing is the clinical capacity. We have each individual agent being formed like this, and then the transition would be from exposed to infected. The agent would send a message. The message you can find up there, treatment request, that will be received by the queue, and the message will be queued. So everyone who sends that request will get a place, like in a, And then if there are enough hospitals and you don't run out of time, nobody wants to wait forever, then you get treated, and at some point you give up and you're not getting treated. You might survive, recover, and then you go back to the original state because it can get multiple times infected. So this is basically mixing the two models, and here we have the hospital model, very similar to what I explained before. It can get complex, but this is a model of the whole world. Yeah, it uses system dynamics because on the one hand this model exists, on the other hand it allows you to save some memory, but then we added a population at one point. So here when we get the output, we mix an agent-based modeling and we model a subset of people and see what they are doing. Now we come to one of the problems, which was computability. And we use a small trick here. We actually use a compound person agent because in this case we were modeling the whole of the US and how they contribute to climate change. And you will find 250,000 people in the US who have kind of the same ideology in comparison to climate change. So you can bundle them and they will make the same decisions over time. In this case, I can run this simulation of the whole of America on my old 10-year-old PC in the office. So that might be an idea that you might consider. It might not work for the epidemiology modeling, but just these are all ideas that I thought you might find useful to consider to overcome these problems. Transparency is also one thing that you can see that these models are very intuitive because they show you what's actually going on inside the model. And they also reach communities that you normally don't reach because you can show it to children and explain to them what the pathway is that people go through. Once you run the simulation, each agent will show you the statistics. Each individual agent, you can look at the statistics. You can see what kind of state they're in. So this one is a polluter. And you can build hierarchical models. So in this case, I have a system dynamics model in that I embed some agents, and each of the agents has a system dynamics model again to make decisions. The reason we did this is because these models were existing, so we were just reusing existing models. And that brings me to the end of my talk.
Thank you very much. Time for a question or two before coffee?
You're all overwhelmed.
I just want a clarification. Can you go back a couple of slides? Yeah, no, the scalability. Scalability of the thing. No, the next one.
This one?
No,
The one that had 1 and 2, 50,000.
the one,
Scale?
yeah.
The scale was
Forward, maybe it's forward. Forward. Next, that's it. So can you elaborate on this? So it looks to me that you're not just looking at individuals anymore, but you are stratifying somehow. Can you elaborate? I
yeah.
misunderstood.
So what I'm doing is I make a group of people who have the same intent and the same behavior, basically. So I'm representing, instead of representing each individual, I have a group that has a mission statement, like I mentioned before. And in this way, I can model the population of the whole of the US, and the decisions they make as a group, because each individual would make a similar decision, will then allow me to see what the pollution is. Yeah.
So just on that note, so I've seen this in action in COVID, where there's a huge scale, but there was some rare people, right? So, and that happened sort of stochastically. So all of a sudden, you know, so they had like one nurse who happened to be a super spreader who worked somewhere, and they represent suddenly 10,000 nurses who happen to be super spreaders who work at a certain hospital and blah. So there's obviously a limit to what you can scale.
Yeah.
Do you want to comment on that?
Yeah. So in the simulation model itself is a slider, and you can then change the scale. And if you have more powerful machines, you can reduce, so you can just summarize 50 people or 100. The alternative would be that actually when something gets interesting, you build another model and you connect those models. So if you want to look at a detailed investigation because something odd happened, you can take 200 agents out, build a separate model, have the inflow of information from the large model, and then observe what's going to happen in that smaller model.
Okay. Thank you.
Jumpy.
I guess that in your collective example you had about 1,200 agents in the end, if you have these collective agents.
Yeah.
How do machine resources needed scale with the number of agents in a model?
I never had a problem with simulating any models because we use software engineering maybe. There's no mathematics behind it. It's all about software engineering. And simulating 1,000 agents is not a problem. Even in my office machine, I do 50,000. That gets critical. But the definition is relatively simple, and you don't need to store that much data. So maybe you have 4 or 5 data points for each agent. If you make large models, you don't make them that complex, so you also simplify. As I mentioned, some models in marketing have only 2 states, but they represent a potential buyer and a buyer, and then the transitions, you need to make some calculations.
I mean that most models can be run on a good laptop, a modern laptop or something.
Yeah. I never had anything else, so, but I don't know, if you want to model these as individuals, then you need some HPC, I guess.
With the collective person agent idea, it seems to me that, for instance, if you wanted to study the start of an epidemic, what you might want to do is have all the susceptibles be represented as collective persons, but the infected to be individuals. Do you think the model could cope with that? And then maybe, as the epidemic developed, maybe you would then move on to also representing, once a significant proportion of the population has a disease, you maybe start representing them as collective person agents. So in this way, you might be able to keep the computations reasonable. Do you think you have that flexibility?
Yeah, I never thought about this, actually. Here's a nice research topic. Yeah, I think it would be possible to dissolve the collective agents when it gets interesting. So your colleague said we have 1,200 agents in this model. If one of them gets interesting, I can dissect it, this individual one. But I've never tried it. So interesting question.
Carl, your arm's dropping off.
So this is all very interesting. Some specific examples of things you can do with agent-based modeling. If you take a step back and talk about what you think of as the prospects for some generic frameworky stuff here, right? So me as a modeler being able to say in a very concise language, I would like an SIR system, hand that to some agent-based model generation software and have that give back to me a, let's say, ready to modify agent-based modeling framework of that particular system. Potentially doing things like, oh, I can do this very clever thing with having a collective susceptibles pool, but then I individually model infectives, that sort of thing. So Is that a clear question?
Yeah. So the one thing you could see in my presentation, we used a unified modeling language, which is a graphical notation which has 28 or something like that different types of diagrams, of which we normally use like 5. So rather than having a programming language, we use this kind of notation. And when we implement it, we have design patterns that help us to make sure that we translate the thing correctly.
Are you yet to the place where you just said when we implement it? What I'm asking is, how close are we to the place where we say, well, here's the UML, machine implement it for me. Possibly the UML plus, hey, I'm interested in this kind of implementation, machine translate it and create that for me.
The examples I showed, the video, is actually done with a software called AnyLogic. So there is a software, it's relatively straightforward, I would say. Also there's NetLogo who supports the state machines nowadays. So there is software that can translate it. It's just kind of if-then rules, basically, to define the states and making sure that you check all the states constantly when events happen. Yeah, so it is possible. And all the models I showed here, they are runnable, basically. And I don't have to do a lot of programming. When I have the transitions, I have to do a little bit of programming because the transitions are very individual and it uses Java for the programming. But other than that, I don't. And there is a personal learner edition, so you could try it out if you like.
Fantastic.
By the way, if anyone wants the slides afterwards,
Great, thanks very much.
I can leave them to you.
Superb, thank you. Okay,
Is there-
so I'm going to suggest, just in the interest of time, so we've got coffee now up until 12 o'clock. Please do continue conversations over a cuppa, and then we'll be back in about 20 minutes. So let's just thank her again. Thank you very much.